It's live now.
Okay, thanks. Okay, I think we can get started. We're a bit delayed anyway. So welcome everyone. This is our first Safari live seminar in October, and I guess the new semester officially. We again have Jawad Haj-Yahya here, who's a principal researcher at Huawei Research Center in Zurich. Before that, Jawad was a postdoc and senior researcher with Safari here for 2 years. And he got his PhD from Haifa University in Israel. And he spent a lot of years as a power management architect at Intel. I hear an echo here. So let me try to turn off some sound here. Okay, that's better. Sorry. Yeah, he spent over a decade, 12, 13 years, right, Jawad, at Intel, doing power management mechanisms. And after that, he spent some time in Singapore at NTU, as well as Astar, doing research on hardware security, as well as other topics. Now, he's going to talk about some of the work that he has recently done on security implications of power management mechanisms in modern microprocessors, especially covert channels that are caused by current management mechanisms due to the execution of power-hungry instructions. He'll give an overview of the power management mechanisms that lead to these new covert channels. And this work was published at ISCA 2021. It's called ichannels. And you can also read the paper if you're interested in further information during or after Jawad's seminar. With that, I think we can get started. Jawad, it's good to have you back for another seminar here. And please go ahead.
Thanks a lot, Onur, for the introduction. And thank you all for joining our Safari live seminar. So please feel free to ask any question during the seminar and at any time. So, and we are looking forward for a good discussions, and I hope the seminar will lead to some high impact ideas and directions. So let's start. So billions of new devices are being deployed each year with the new services and features that are driving a high demand for high performance microprocessors, which often have high power consumption. Despite the failure of Dennard scaling and the slowdown in Moore's law and the high power density of modern processors, power management mechanisms have enabled significant advances in modern microprocessor performance and energy efficiency. So yet current power management architectures also pose serious security implications. This mainly because functionality rather than security have been the main consideration in the design of power management mechanisms in commodity microprocessors. So in this seminar, we present an overview of state-of-the-art power management mechanisms used in modern microprocessors. And then we introduce our recently revealed set of vulnerabilities, ichannels, and a set of covert channels that exploits multi-level throttling techniques used by current management mechanisms in modern processors. And finally, we propose multiple practical mitigations to protect against ichannels in modern processors. There are several attacks that exploit power management vulnerabilities of modern high-performance computing systems. For example, catching the flu creates two attacks that significantly degrades the power efficiency by increasing by inserting hardware trojans to the power management unit. And the ClockScrow propose an attack that infers the secret keys by enforcing anomalous frequency and voltage in the DVFS and inducing timing errors. Other work, which is DVFS covert, creates a covert channel between Trojan and spy processes by modulating the processor operating frequency with the help of power governor to to covertly leak data. Then finally, a capsule creates a covert channel between independent FPGA boards in a data center by using the power supply unit without physical access to the board. So next, I will present part of our ISCA 2021 work related to this topic and compare it to recent works. So the work is called ichannels, exploiting current management mechanisms to create covert channel in modern processors. So first, I will give a high-level overview of the topic. So current management mechanisms throttle instruction execution and adjust voltage and frequency to accommodate power-hungry instructions, PHIs. These mechanisms may compromise a system's confidentiality guarantees. Our goal is to first to understand the throttling side effects of current management mechanisms, and secondly, build high capacity covert channels between otherwise isolated execution contexts. And finally, practically and effectively mitigate each covert channel. So we characterize the variable execution time and the frequency change due to running PHIs. We actually propose ichannels, which is a new covert channels that exploit side effects of current management mechanisms on the same hardware thread across co-located simultaneous multi-threading threads and across physical cores. So in 3 generations of Intel processors, ichannels provide 2 times that of PHI's variable latency-based covert channel and 24 times that of power management-based covert channels. And I will give a brief overview on client processors architectures. So in many recent processors, CPU cores share the same voltage regulator and clock domain. A central power management unit controls the voltage regulators using an off-chip serial voltage identification interface. The clock phase locked loop using an on-chip interface, and each CPU has a power gate for the entire core, and each SIMD unit has a separate power gate. So the relationship between load voltage VCC, load supply voltage VCC, and the current ICC under a given system impedance R load line is VCC load equal VCC minus ICC times R load line. Basically, as shown in this picture, so the power management units adds a voltage guard to VCC to a level that keeps the VCC load within limits. So above the minimum functional voltage VCC mean, under the most intensive load power virus with a current of ICC virus. And below the maximum operational voltage VCC max under the lightest load leakage with the current I leakage. For loads with the current lower than a ICC virus, the voltage drop is smaller than when running with a power virus, resulting in a higher load voltage than necessary, which leads to a power loss that increases quadratically with the voltage level. So I will now discuss the motivation and the goal of our work. So prior works have multiple limitations. So NetSpectre exploits the variable execution time of PHIs to create covert channels. NetSpectre has mainly 3 limitations. So first is established only between 2 execution contexts of the same hardware thread. And secondly, it uses only a single level throttling side effect. Thread is throttled or thread is unthrottled. And finally, it does not identify the true source of throttling. Basically, NetSpectre hypothesized that the throttling is due to power gating of PHI's execution unit. Then TurboCC exploits the core frequency throttling when executing PHIs to create a cross-core covert channel. TurboCC has two limitations. So first, it focuses only on the slow side effect of frequency throttling that happens when executing PHIs at only turbo frequency. And secondly, it does not uncover the real reason beyond the vulnerability. Basically, TurboCC hypothesizes that the frequency throttling is due to thermal management of the processor. So any questions so far? Okay, so basically recent works propose limited covert channels and use inaccurate observations. So our goal is in this work is to firstly experimentally understand the throttling side effects of current management mechanisms in modern processors to gain several deep insights into how these mechanisms can be abused by attackers. And secondly, build high capacity covert channels, ichannels, between otherwise isolated execution in contexts on the same hardware thread across co-located simultaneous multi-threading threads and across different cores. So then practically and effectively mitigate covert channels caused by the current management mechanisms. So now I'll present the throttling characterizations. So we experimentally studied three modern Intel processors, Haswell, Coffee Lake, and Cannon Lake. We measure voltage and current using data acquisition card in IDAC, and here is the picture of our system. So we study the impact of power-hungry instructions, PHIs, on CPU core supply voltage, VCC. Basically, we track the VCC change during an experiment on two-core Coffee Lake system, executing code that includes AVX2 phases. VCC increases once the CPU core begins executing AVX2 instructions. The more cores executing AVX instructions, the higher the VCC. So voltage emergency avoidance mechanism prevent the core voltage from dropping below the minimum operational voltage limit when executing PHI. We use the following system. So a single core Coffee Lake desktop CPU operates at turbo frequency of 4.9 and 4.8 gigahertz at two-core Cannon Lake mobile CPU operates at turbo frequency 3.1 and 2.2 gigahertz. So we execute non-AVX and AVX workloads while measuring current and voltage. So the bars with the green border are projected. Here are VCC max and ICC max limits of each system. So for both desktop frequencies, ICC is below the ICC max limit. VCC will exceed the VCC max limit when executing AVX2 code at a frequency of 4.9 gigahertz. And for both mobile frequencies, VCC is below the VCC max limit. But ICC will exceed the ICC max limit when executing AVX2 code for frequency of 3.1 gigahertz. So contrary to the state-of-the-art work hypothesis, basically the core frequency reduction that directly follows the execution of PHIs at the turbo frequency is not due to thermal management. Basically, it's due to maximum instantaneous current limit, ICC max, and maximum voltage limit VCC max protection mechanisms. So we studied that we studied the time it takes to open the AVX power gate of Coffee Lake by comparing it to Haswell system. Basically, Haswell system does not have AVX power gate. So when running AVX2 instructions in a loop consisting of 300 AVX instructions that use registers, the first iteration of the loop running the Coffee Lake is more than 8 nanoseconds longer than the other 2 iterations. For the Haswell system, all iterations have nearly the same latency. So the following graph shows AVX throttling with a zoom in into power gating in the right side. So the AVX power gating feature have approximately 8 to 15 nanoseconds of wake-up latency. It's about 1% of the total throttling time when executing PHIs, which is greater than 10 microseconds. So contrary to the state-of-the-art work hypothesis, power gating AVX execution unit it accounts only for 0.1% of the total throttling time observed when executing PHIs. The majority of the throttling is due to voltage transitions.
So Jawad, I have one question in the previous figure. If you go to, here you have both Coffee Lake and Haswell, right?
Right.
In Coffee Lake, clearly there's a difference, but in Haswell, is there no throttling?
Yeah, there is a throttling, but the throttling is due to the voltage transitions, which is in 10 nanosecond of granularity, 10 microsecond of granularity. But in Coffee Lake, there is additional throttling in the level of nanoseconds that happens due to opening the power gate.
Okay.
So,
okay.
Yeah, so this is the difference. Yeah.
Okay. That makes sense. That's clear now.
And any other questions? Okay. So, we execute one of 7 iteration types in a loop, followed by a 512-bit heavy loop. A heavy loop, heavy instructions are instructions that require floating point units or any multiplications. The throttling period of the 512-bit heavy loop increases when the computational intensity of the instructions executed in the preceding loop decreases. So the lower the instructions computational intensity in the preceding loop, the lower the applied voltage guard band to this instruction. So hence, the 512 heavy loop requires more time to increase basically the voltage to the required level. So we observed that there are 5 levels from level 1 to level 5 corresponding to the computational intensity of the instruction types. So current management mechanisms result in a multi-level throttling period depending on the computational intensity of the PHIs. So we study the source of the throttling and the microarchitecture impact. We track the number of micro operations, UOPs, that the core pipeline delivers from the front end to the back end during the throttling and non-throttled, during the throttled and non-throttled AVX loops. So the front end does not deliver any UOP in approximately 3/4 of the core cycle, even though the backend is not stalled. So the core uses a throttling mechanism that limits the number of UOPs delivered from the front end to the backend during a certain window. And we found that this throttling mechanism affect both SMT threads. So contrary to the state-of-the-art works hypothesis, the 4 times core IPC reduction that directly follows the execution of PHIs is not due to the reduction in the core frequency by 4 times. It's rather because of the that the cores blocks the front end to the back end UOP delivery during 75% of the time. And this throttling mechanism affect both threads in SMT core. So now I will explain the covert channels of ichannels.
Jawad, before you move on,
Yeah.
I have another question in the previous slide. This is very interesting, for sure. But I guess why does it affect both threads in the SMT core? You probably have some insight.
Yeah, I think it's related to the way that Intel implements this throttling mechanism. So I think they went to the easy way to throttle it just for the entire threads without selecting per which thread is running the the PHIs in the core. So maybe it's like a implementation consideration, but does not have to be like this. Like one of the mitigations that we propose is just to make this implementation more efficient.
Yeah, by making it thread aware, you don't need to affect all of the other threads that are running in the same core, right?
Right, exactly.
Okay.
Okay, so now I will explain the covert channels of ichannels. So the threat model is basically consists of 2 malicious user-level attacker applications, sender and receiver, which cannot communicate through an overt channel. We build 3 high throughput covert channels between sender and receiver that exploit the throttling side effects of current management mechanisms on the same hardware thread, across SMT threads, and across cores. So each covert channel sends 2 bits from the sender to the receiver in every transaction. Each covert channel should wait for reset time before sending a new transaction. Basically, we demonstrate that the covert channels of ichannels on Cannon Lake real system. So now I will talk about each of the covert channels in more details. So the first covert channel is the ICC thread covert established on the same hardware thread. So ICC thread covert channels exploit the side effects of multi-throttling thread, which is basically once executing an instruction with the high computational intensity, it results in a throttling period proportional to the difference in the voltage requirement of the currently and the previously executing instructions, as illustrated here. So the thread executes scalar instructions with IPC of 2, and N0 loop starts executing with IPC of 1. So N0 loop is throttled while ramping the voltage VCC, and once the target VCC is reached, the throttling is stopped. So when 512 heavy 512 beat heavy loop is executed, it's first throttled while ramping the VCC to accommodate the 512 beat heavy, basically heavy instruction. And T0 throttling period depends on the computational intensity of N0 loop. The remaining voltage required to execute 512-bit heavy instruction depends on the previous VCC level that was reached by when executing N0 loop. on the processor. So ICC covert channel exploit the multi-throttling thread side effect to build a covert channel between sender and receiver. So the sender execute a PHI loop with the computational intensity level from level 1 to level 4, depending on the value of the two secret bits it want to send. And the receiver can infer the two bit sent by the sender by measuring the throttling period of the 512-bit heavy loop. The higher the power required by the PHI loop executed by the sender, the shorter the throttling period experienced by the receiver will be. So the second covert channel is
Jawad, maybe before you go to the next one, I have one more question.
Yeah, sure.
Can you go to 2 slides before or the previous slide where you characterized the throttling period? Yes, this one. So if I understand this correctly, you're showing the throttling period that is experienced by 512-bit heavy loop, right?
Right, yes.
And if the previous instruction, like the inst 0, as you call it, is the same, then there's no throttling.
Yes, exactly.
Okay. It also is of the same kind, let's say 512-bit heavy. But if the previous instruction is very simple, like 64-bit, then the throttling period is much longer, right?
Yes, then you will need the instruction will need the full voltage transition.
I see. Okay, so basically it's really about how long the voltage transition takes to execute the heavy 512-bit heavy instruction, right?
Right, exactly.
And of course the difference, the voltage differential between the prior instruction and this instruction, and there are 5 different levels, let's say, of that transition that may happen depending on the type of the previous instruction.
Right. Yes, because like according to our characterization, this mechanism depend on the voltage level that currently happening on the processor. So if previously a heavy instruction was executed, then the next heavy instruction will not suffer from throttling because it's in the same level of voltage. And if just scalar instructions were executed before this PHI instruction, so then you need to wait until the voltage is ramped in order to run the PHI instruction without throttling.
Yeah, makes sense. Just to make sure, the scalar, when you say scalar, I think in this figure on the bottom right, 64-bit instructions are scalar, right? They're not vector.
Right, exactly.
But everything else is vector, AVX?
Yes, every other is vector with different levels.
Okay, so yeah, some of them are narrower and some of them are wider in terms of bit width. What is the distinction between light and heavy?
Yeah, so like the heavy basically is instructions that execute a floating point or multiplication, and the lighter is the rest.
Okay. Yeah.
Like
so
add instruction is for example, or is light instruction.
So in general, heavy instructions and wider instructions require more voltage to execute. They're more power hungry, basically.
Right, exactly, because they have higher CDIN or like dynamic capacitance, so they need more current, and they have more voltage drop. Then you need to raise the voltage for this.
Okay, I guess yeah, this is very interesting, certainly. But and this is data from real processors, right?
Yes, exactly. The characterization was done in real processors and with measurements directly on the system.
Okay. One more question. Is this so there are certainly 5 throttling levels, but can there be more, or that requires some exhaustive measurement for different types of instructions to figure out if there are more, right? Do you know if there are more, or did you do?
Yeah, actually, like there may be more, but like I think the implementation merged part of these instructions together. For example, if you take a look, if you take and add instructions that like you can see, for example, the 256-bit heavy instructions and the 512-bit light instructions, they are very close to each other.
Mm-hmm.
So we consider that one level because it's hard to differentiate the difference between them. And I assume that various instructions will have different levels of capacitance, but because of the limitations of the measurement tools, we will not be able to distinguish between them.
Mm-hmm. Yeah, that makes sense, I think. I'm actually curious, for example, if there's any difference between scalar instructions. There's 64-bit that you show over here. What if you're using something 8-bit, let's say?
Yeah, I think that there are also some granularity between these instructions. I have a different study in my PhD that I characterize also these instructions called energy per instruction, and there are differences all between them. Mm-hmm. But here we treat them as one one value, which is the maximum between all of these instructions. Mm-hmm. But definitely, like you can measure more granularity in these kind of instructions. Mm-hmm. And also, if you go to 8-bit, you will have lower instructions. But it also depends on the implementation. Like if the implementation is using these instructions, for example, if you they have them as like the first 8-bit are in use and the other ones are 0, then you will have less dynamic capacitance in this case, and you will have lower power.
Mm-hmm. Okay, that makes sense. Thanks.
Yeah. Okay, so let's move to
Hi, Jawad. There are a couple of questions in YouTube. Maybe it's a good time to ask them. So the first one is similar to instructions. Does a heavy thread affect the execution of next thread?
Like if a heavy thread will affect the other, yeah, I think. Okay, so if you have a heavy thread and after that lighter thread is coming after context switch, for example, then the lighter thread will be affected at some level, because like we figure out that there is some reset value for the execution. It's about like 600 microseconds until the mechanism will reduce the voltage. 650 microseconds in this level. So like all the instructions, so let's say that you have a high power instruction, a high power thread that's running now, and then having a context switch happens, and then you have a light thread that's coming in. This thread will suffer from not throttling, it will suffer from high power, because you will have higher voltage for that thread, and until some stage, until the voltage will be reduced to that thread.
It makes sense. Thanks. And the next question is, does Intel Cannon Lake's 10 nanometers transistor size has something to do with a limit to prevent possible effects like quantum tunneling?
I'm not sure I understand the question here. Like it's, I think it's not related to. Can you repeat the question? Like
Yeah, the question says, does Intel Cannon Lake's 10 nanometer transistor size has something to do with a limit to prevent possible effects like quantum tunneling?
I'm not sure I understand the question. So
yeah, maybe the author of the question can clarify this in the comments.
Yeah. Okay. Because I think it's not related to what they are talking, but like let's clarify this, and maybe we can answer this question.
Thanks, Jawad.
Okay. So let's move to the second covert channel, which is called ICC SMT covert. So ICC SMT covert channel exploits the side effect of multi-throttling SMT. In this side effect, when a thread is throttled due to executing PHIs, the co-located SMT thread is also throttled. We discover that co-located hardware threads are throttled together because the throttling mechanism is in the core pipeline blocks the front end to the back end interface during the 3/4 of the throttling period for the entire core, as illustrated here. So the thread executes a scalar threads execute scalar instructions with IPC of 2. And T0 starts executing N0 loop with IPC of 1, and T1 starts executing 64-bit loop with IPC of 1. T0 and T1 loops are throttled while ramping up the voltage, the VCC. And once the target voltage is reached, the throttling is stopped. T1 throttling period depends on the computational intensity of N0 executed by T0, which depends on the VCC level which the processor needs to increase the supply voltage. So ICC SMT covert exploit the multi-throttling SMT side effect to build a covert channel between sender and receiver. The sender executes a PHI with the computational intensity level, and depending on the value of the two secret bit it wants to send. And the receiver can infer the 2-bit sent by the sender based on the measuring of the throttling period of the 64-bit loop. So the higher the power required by the PHI loop executed by the sender, the higher the TP, the throttling period experienced by the receiver will be. Yeah, so the third covert channel is ICC cores covert established across different physical cores. So ICC cores covert channel exploits the side effect of multi-throttling cores. In this side effect, when two cores execute PHIs at similar times, the throttling period are exacerbated proportionally to the computational intensity of each PHI executed in each core. Basically, this increase in the throttling period is because the power management unit waits until the voltage transition of core A to complete before starting the voltage transition of core B, as illustrated here. So T0 and T1 in core 0 and core 1 start executing N0 and 128-bit heavy loop, both with IPC of 1. T0 and T1 loops are throttled. Once T0 target VCC reached, T0 throttling is stopped. T1 continue to be throttled since the PMU will wait until will not handle basically the T1 voltage transition until T0 voltage target is reached. And T1 throttling period depends on the computational intensity of N0, which determines a VCC level to which the PMU needs to increase the supply voltage before handling the T1 voltage transition. So ICC cores covert exploit basically multi-throttling cores side effect to build a covert channel between sender and receiver. The sender executes a PHI loop with the computational intensity level depends on the values of two secret bit it wants to send. And the receiver can infer the 2 bits sent by the sender based on the measured throttling period of the 128-bit heavy loop. The higher the power required by the PHI loop executed by the sender, the higher the throttling period experienced by the receiver will be. So now I will present our evaluation of iChannel.
Jawad, I think I have one more question. Again,
Yes,
on the characterization of the throttling period across the cores. Yeah, in the previous slide.
Yeah, here.
Yeah, here, exactly. So here in core 1, you choose 128-bit heavy instruction, right?
Yeah,
and there's a constant throttling period for that. Is that correct?
right, exactly.
Okay, that does not depend on anything else?
Yes, it does not depend on anything else. Like it's a constant because like this is the voltage level that the process like the processor or the PMU needs to raise the voltage
to that instruction
yes.
to execute that instruction. Okay, but you could also pick some other instruction, right? Type.
Right, exactly. Yeah. Yes.
Then
right.
then the value of that or the length of that throttling period, the blue portion of the graph, let's say, would change, right?
Yes, exactly.
Okay.
Exactly. Yeah.
Okay.
Right.
Okay, that makes sense. And you're still looking at the relative difference between instruction 0 and this 128-bit heavy.
Right, exactly, because like the PMU will not handle the execution of the I mean the ramping the voltage for the other instruction until it finished the like the ramping of the first instruction. There are multiple like proposals to fix this, but like this is related to something in the mechanism, because this is a shared voltage regulator. So this limitation exists.
Sure. So the fundamental reason here is that the voltage regulator is shared between the different cores, right?
Right. Exactly.
So if you have isolated or separate voltage regulators on a per core basis, this particular covert channel 3 will go away. Am I correct?
Yeah, yes, you are correct. Like basically, one of the mitigations that we propose is just to have a separate voltage regulator, like for example LDO or IVR, and this will solve this specific covert channel.
Okay. Yeah. Of course, there are trade-offs associated with per core versus shared voltage regulators, like cost.
Yes, exactly. And we have a paper also on that, like in I think in it Flix, where we compare these voltage regulators in terms of cost and the area and so on, and performance also. Yeah,
exactly. And you presented that in the previous seminar. So
exactly.
Right. Okay. Yeah, maybe we can have a more of a discussion of that when we get to the solutions, mitigations.
Yeah, sure, perfect.
Okay, thanks.
Yeah, sure. Yeah, so now I'll present our evaluation of iChannels. So first, I will present our methodology. So we evaluate iChannels on Coffee Lake and Cannon Lake processors. We tested ICC covert and ICC cores. We test ICC thread covert and ICC cores covert on both processors, but the ICC SMT coverts only on Cannon Lake, because the Coffee Lake does not support the SMT option. So our main workload are proof of concept code of each of the 3 covert channels, and we compare iChannels to 4 recent works that exploit different power management mechanisms of modern processors to build covert channels. So we compare ICC thread covert against NetSpectre, the state-of-the-art work that exploit variable latency of PHIs to create a covert channel between 2 execution contexts running on the same hardware thread. The NetSpectre covert channel can send 1 bit per transaction, while our ICC thread covert channel can send 2 bits per transaction. So we compare ICC SMT and ICC cores covert against DFS covert, Turbo CC, and PowerT, the state-of-the-art works that exploit different power management mechanisms of modern processors to build covert channels across different across cores and SMT threads. ICC SMT covert and ICC cores covert throughput is 145 times and 47 times and 24 times the throughput of DFS covert, Turbo CC, and Power T respectively. The three workloads exploit a slow mechanism compared to the current management side effect that our ichannel exploits. So we have more results on the paper. For example, we propose practical hardware and software techniques for the mitigation of ichannel covert channel. So we have one of the proposals have fast per core voltage regulator, and the other option, the other mitigation, basically improve core throttling and use secure mode of operation. So this table shows the effectiveness of the effectiveness and the overhead of each proposed mitigation technique. So maybe we can talk more about this in details here. Like to mitigate the thread, like the ICC thread covert channel, we need basically fast per core voltage regulator. It will mitigate partially the this covert channel because it will do the transitions faster and the voltage transition faster, and this will reduce the time that the attacker can exploit in which the threads are throttled. So as we can see here in the table, like we have a per core voltage regulator and improved throttling and the secure mode. So per core voltage regulator will mitigate the throttling. I mean the ICC thread covert partially, and it will also will have partial effect on the ICC SMT covert, but it will mitigate the ICC cores covert because each core has its own voltage regulator, and the transitions here will be independent. And we mean by improved throttling, basically we talked about the throttling of the SMT, which happens for like SMT cores. Like once one thread is running a PHI power hungry instructions, then the other thread on the SMT core is throttled. So one option to mitigate this is just to have a pair like thread aware or a throttling instead of just throttling both of the threads in the core. Yeah, so this will solve the issue with the SMT, but the other like I mean covert channels, ICC thread covert and ICC cores covert, this mitigation will not affect them. And if we take a look at the third one, which is the secure mode, basically what we propose here is to have a secure mode which disable this feature. Like I mean the feature of preventing ICC max throttling or I mean this power management protection mechanism. What we can do is once we have a secure mode, the processor enter to some secure mode, then the processor can go to the worst case like power level or voltage level, and this will affect the frequency of the running threads. But we will have some determinism, like the thread will not be throttled in this case once they are running. So this like the overhead of this is that we'll have between 4% to 11% additional power once we are running on that mode. Yeah. So and this additional power also depends on how many cores are running and so on. But it's like a rough some rough estimations. So as we can see, like the most effective way is just to try to disable these power management mechanisms in order just to have less to reduce the attack surface. We also like the focus of the work was not mainly on the mitigations, but we can think of additional like ideas for mitigation, mitigating this kind of covert channels. So actually, I think like more effective ways of mitigating this kind of covert channels can be explored, and I think this issue is still open because although secure mode is effective, I'm not sure it's I think it's not scalable for many cores and for we are talking here about client system, but what about, for example, servers that you'll have tens of cores, so raising the voltage for them for all of them will have significant like performance and power impact.
Yeah, I agree with you, Jawad. I think there's room for improvement in the mitigation mechanisms for this sort of voltage current related covert channels, right?
Mm-hmm. Yeah. Right.
So just to understand this a little bit more, for the secure mode, you're suggesting that when you're running something, let's say security critical, where you don't want to leak information, you enter this mode where you essentially don't allow you run at the maximum voltage and maximum current to execute any possible instruction, right?
Yes, exactly. Like once you enter to this mode, like let's say you have this let's say we have an instruction that indicates this that we are entering to this mode. So then the processor will switch to a mode that which is the worst case. Mm-hmm. I mean, worst case here corresponding to the highest power consumption, the highest PHI power consumption, like for example 512 bit instruction, which is the raising the voltage to the maximum. And then any instruction that will be executed will not be throttled, and this way you will not, you don't need to have this mechanism, or it's throttling basically.
Sure. Yeah, makes sense. I think. Yeah. Yeah. Of course, it comes with additional overheads, as you said, or reducing the frequency significantly to accommodate.
Right.
That,
exactly. Yeah. Exactly. And again, this is just for the client processors. Maybe like again for servers or the newer client processor that have more cores, this will be more painful mitigation.
Yeah. But maybe you can potentially partition the chip into different areas and apply secure mode in the partition where you're running the security critical application, right?
Yeah, actually, this is a good idea. Like. This can work, and but you need also to be like the power manager to be aware, or the schedule to be aware where to schedule the threads, and like which ones are secure and which ones are not, and so on. But like for this also you need I think like the scheduler to be aware for example voltage regulators and so on. But as I said, like this area, like we can explore it more. But this is one of the ideas that you mentioned, which can work.
Yeah, sure, makes sense. I think there's certainly room for further exploration. One thing I also wanted to understand here is with the first technique, per core voltage regulator. Clearly, it adds some more cost, as we discussed earlier. But why do you think it reduces the vulnerability for ICC thread, I guess covert channels on the same thread and across SMT threads? You say partially in this table, right?
Yeah, actually, this is not appearing from the table, but like in the paper we discuss it. What is missing here? The point is that per core voltage regulators, we propose like either LDO or IVR, and they have they are coming with a high slew rate, like of the voltage. Like changing the voltage is very fast relative to the voltage regulator that we have in this characterized architecture, which is like Cannon Lake or Skylake, which is the external voltage regulator. So these voltage regulators, like LDO and IVR, which are integrated voltage regulator per core, they are fast. So the window of throttling is lower than our system. That's why we are mentioning that it's partially, like it will reduce the like the attack surface.
Yeah. Do you have a guess as to what that window is? Because in the previous, I think, characterization, you have windows as long as, let's say, 20 microseconds, right? What would be the window when you have a fast per core voltage regulator?
Yes, so like it can be less than 1 microsecond.
Okay.
But also it depends on the implementation of the DVFS. Like one of the slides that we show that also in Haswell, this issue of Haswell, which have IVR per core, this issue of throttling exists, but it's less less than the system that we have, which is Cannon Lake. And it's because of the faster transition of the voltage. But there is also in the implementation of the DVFS mechanism between the firmware and the FSMs that handle this transition, there are some limitations. It is not just the voltage regulator, but the voltage regulator part will be reduced. Yeah. So in recent Intel processors, like there is a published paper on that. It's called IDVFS. They have a very fast DVFS mechanism, which also can be a good mitigation for this kind of covert channels.
Yeah, basically that will also reduce the vulnerability window, right? By keeping the throttling period shorter.
Yes, exactly. But it will not eliminate it, because of that we are talking about partially. Like if like an attacker try many times, he will succeed at the end.
Yeah. If you have a probabilistic attack, since these are probabilistic attacks for measurement anyway, you can build confidence in your measurements over time, right?
Right. Exactly. Yeah.
Okay. Cool. Thanks.
Yeah. Sure. So, any other questions on this part of the mitigations? Okay, so let me quickly conclude my talk. So basically, current management mechanisms throttle instruction execution and adjust voltage and frequency to accommodate power-hungry instructions. These mechanisms may compromise a system confidentiality. So our goal is to understand the throttling side effect of current management mechanisms and build high-capacity covert channels between otherwise isolated execution contexts, then partially and practically and effectively mitigate each covert channel. So we characterize the variable execution time and the frequency change due to running PHIs. We observed 5 different levels of throttling in real systems. We propose ichannels, and new covert channels that exploit side effects of current management mechanisms on the same hardware thread across SMT threads and across different cores. And on 3 generations of Intel processors, ichannels provide a channel capacity 2 times that of PHI's variable latency-based covert channels, and 24 times that of power management covert channels. So for many more details, please read our ISCA 2021 paper, and feel free to contact us on any question. So now I will conclude the seminar. So in this seminar, we provide a detailed overview of the state-of-the-art power management mechanisms and security vulnerabilities of power management mechanisms in modern processors. We conclude that power management and the resulting security implications are critical and exciting areas to research to make modern system both more energy efficient and high performance. So thank you for your attention. And again, please feel free to approach me if you have any question or a topic that you would like to discuss on this area or other areas related to power management and security.
Hi, Jawad.
Yeah.
Actually, there is a question on YouTube now that I want to ask. I think it's an interesting one, actually. So considering that vector instructions often act as PHYs, can we replace vector instructions with loops of scalar instructions? And so this would definitely reduce the speed and we would lose performance, but can it be considered safer for iChannels?
Yeah, I think it's a good idea. So this is basically one of the mitigations that we can propose here. By the way, there is also a patent on this from, I think it's from Intel, like to divide like vector instructions to multiple other vector instructions, or to multiple scalar instructions to, but it's not to mitigate this issue. It's like to reduce power, or in some cases. But definitely this idea will work. It comes with implications on performance, but it can basically like mitigate this issue.
Okay, that makes sense. Thank you.
Yeah, thank you. Are there any other questions?
Maybe I'll maybe I'll ask a question. I think before Girai asks something. So these are certainly very interesting attacks, Jawad, but how practical are they?
Yeah, actually, these kind of attacks, once you show a proof of concept, so they can be exploited basically by an attacker that have access to the system. So like some of the we didn't in our work, we didn't show a real world attack, because like the previous works already did that. They showed some like practical and real world attacks. So what in our work, just we focus on the mechanism and on the characterization instead of like replicating the previous the prior works attack. But they are practical and can be exploited by attackers. Once they are in the system, an attacker can exploit them.
So when you say they're in the system, they need to be able to execute software, right?
Exactly.
So it's user level. They don't need physical access or anything.
Right. It can be remote access also. Yeah.
Okay. Yeah. Okay. And I think in the paper you analyze the noise effects, like system noise, like interrupts, context switches, etc.
Yeah, right. Definitely, there will be a noise in the system. And by the way, all of the like covert channels that exist today, they have some level of noise, either because of other threads that are running, or because of the the attack vector is narrow. Like as we discussed here, for example, the window that of the throttling can be narrow as tens of microsecond, and maybe it can also be less than 1 microsecond. So you need to just tune the system or your attack based on that window. So there will be definitely much noise, but like we show in our analysis that we noise in many cases you will be able to perform the attacks with reduced noise.
Mm-hmm. Yeah, makes sense. And I think prior work has also developed techniques to tolerate the noise by executing multiple times and in other ways as well, right?
Right, and error correction code, for example, one of the options to basically to mitigate these noise issues. Yeah.
Mm-hmm. Okay. Yeah.
Mm-hmm.
Okay, thanks. Yeah, maybe Giray, Louise, and others have some questions too.
So we had a question earlier about Cable Lake's 10 nanometer transistor size. Sorry, Canon Lake's 10 nanometer transistor size, and we were expecting some clarification, and it came. So the question is about the effect of reducing the transistor size on the energy consumption of these instructions. So maybe you can elaborate more on like the how power consumption of this power hungry instructions and other instructions vary across different transistor sizes. Maybe I think that's more relevant.
Yeah, sure. Yeah, now it's more clear. So like, but basically the power hungry instructions and then will still be power hungry also in like in the newer process generations, because what we are talking here about is the relative power between instructions. So, and which is like reflected in the CDIN, or the dynamic capacitance. So like if you have 128-bit vector instructions, they will still have less power than the 512-bit instructions, and the power is relative. So the voltage level that you need to have for every and each instruction will still be different. One of the differences here is that like the granularity of voltage or will be more finer with I think with the process technology, because like the differences in the voltage will be less in newer process technology nodes.
So maybe as a follow-up, would this relative difference be much smaller, so that it's impossible to, or maybe not practical to detect this voltage difference when, let's say, transistor size reduces to like very small technology nodes, like I don't know, maybe 1 nanometer, right, or like maybe 0.1 nanometer, if you go to that kind of extremes, if it's possible at all. So would you expect this voltage difference or power consumption difference to be still significant enough to induce this kind or perform this kind of attacks, for example?
Yeah, I like for again for the most advanced like process technology, there will still be the difference in dynamic capacitance between these instructions. Again, for example, if you take 512 vector instructions and you take 256 vector instructions, you'll still have double the size of the registers, and which will be reflected in much more, like in at least 2x the capacitance of the other instruction, which will lead to at least two times the dynamic capacitance of the 512 instructions compared to 56 instruction. Like it's independent of the process technology. It's just the structure of these instructions will be doubled, and it's not like related to process technology. But what's related to process technology, again, like it's the amount of the voltage difference. So like the granularity of voltage, for example, today in most processors is 5 millivolt granularity, and new technologies or new like voltage regulators can have finer grain voltage levels, but some of these voltage level can be adequate for some of the instructions, as we saw in the levels. Like some of the levels are, for example, the 512 bit heavy instruction and the 256 bit heavy instruction and the 512 light instruction are having the same voltage, or nearly the same voltage. It's because they are very close to each other from dynamic capacitance, and also the voltage is the voltage difference level is narrow relative to the dynamic capacitance of these instructions.
Yeah, I think that makes perfect sense. Thank you very much.
Yeah, sure. So any other questions, Giray?
I think we don't have much more questions in YouTube, but maybe in the audience, some other people want to ask questions. I don't know.
Hi, Jawad. Maybe you can comment a little bit on the applicability of these covert channels on other processors other than Intel.
Yeah, so like in our paper, we focused on Intel processors, but the mechanisms or similar mechanisms exist in other processors like ARM and AMD. For example, in a paper from 2020 of AMD Zen 2, they talked about a similar mechanism that predicts like vector AVX256 instructions and throttling the instructions before changing the voltage or before raising the voltage, and then they execute the instruction and throttle. But we actually didn't characterize these systems because this will take significant effort to do that, because it depends also on the implementation of the throttling mechanism themselves and other effects. But I think like follow-up works can focus on this, and definitely this kind of throttling mechanisms and power management, like to reduce the power for typical instructions versus AVX instructions, exist in all modern processors.
Yeah, so basically probably only requires some engineering efforts to replicate these covert channels on other processors, right?
Yes, I think so. Like I'm not sure about if all of them can be replicated, because again, like for example, the SMT, the ICC SMT covert, which exploit that once one thread is throttled, the other SMT thread is also throttled. Maybe this is a specific implementation of the architecture that we're talking about, which is Intel. Maybe the other architectures implement already what we propose in the mitigation, which just throttle the thread that is is executing the high level instruction, the high power instructions. Sorry. So like I'm not sure if all of all of the covert channels can be replicated, but definitely like most of them can be. One of the covert channels, like other covert channels that I'm sure that will not be able to replicate, for example, on AMD, which is the ICC cores covert, because like if we are talking about Zen 2 and Zen 3, they already have the LDO per core, and so I'm not. I don't expect the effect of changing one voltage in one core to affect the other core, but like I'm not fully sure, but it can be checked. Because why I'm not fully sure, because like sometimes the voltage change on one core affect the external voltage regulator, which is shared between all cores in the LDO topology. So it depends on the implementation, like how AMD implemented this voltage regulator. So I think it will be exciting area to for follow-up work on these side effects, on these side channels or covert channels.
Very good, thanks.
Mm-hmm. Thank you.
Yeah, Jawad, maybe I have a question related to the methodology. So if you go back to the slide where you showed the infrastructure you used to evaluate this, clearly this work requires some infrastructure, right?
Yeah, this one?
Yeah, I think you had, well, maybe it's in the paper, but there's a picture of the infrastructure, right?
Yeah,
or it's earlier. Okay, yeah, it's earlier.
Yeah. It's in the characterization, yeah.
Exactly, yeah. So clearly this work requires some infrastructure building to measure power and the throttling periods. Maybe you can describe what it takes to do that so that other people who may be interested can know what they need to do if they want to, for example, apply it to some other processor.
Yeah, this is a very good question. Like one of the reasons also that we choose these processors like Coffee Lake and Cannon Lake, the measurements were basically done. I mean, the voltage measurements and the and the current were done on these processors. Is basically because these processors have external voltage regulators for the cores. Like what we need here is a measurement tool that like is attached to the input voltage to the CPU, and you have a sense resistor to measure the current through that voltage regulator through that sensor, and then this data is reported to the host computer that collects the data. So it's a known way to do a measurements for voltage regulator for processor. This measurement tool is very accurate. I think we cited the accuracy. It's more than 99% accuracy, and the granularity, the bandwidth is very high for this NI DAC. These systems can like one of the good thing about the processor that, or one of the easy way to do these measurements is because we have again external voltage regulator, and we don't have internal voltage regulators for the Coffee Lake and the Cannon Lake systems. But things may be more complicated once you have integrated voltage regulators, because knowing the internal voltage of each core once you have integrated voltage regulator is very hard, and for that you need some DFT designed for testing capabilities, which is normally exist for the processor vendors, it's very hard to observe that from outside, unless your processor is reporting this data to some register inside the processor, where you can read that data from software. Yeah, so this is in general like how we did the measurements. Again, like characterization of these processors was relatively easy, but more advanced processors from Intel and AMD and maybe other vendors will be harder to do per core voltage characterization without DFT capabilities from the vendors themselves.
Yeah, that makes sense, I think. Thanks. Yeah.
Mm-hmm.
I think one related question which may be interesting at multiple levels is how does temperature affect all of these measurements?
Yeah, actually, temperature will like different temperatures will affect the voltage. Sorry, the power measurements, and for this we need to have the system with the same temperature all the time. That's why we once we run one test, like one of the effects of these high power instructions that they increase the voltage and the power and increase the temperature, and subsequent measurements will be affected by the previous measurements. So we need to put some spare time between two measurements in order to cool down the system. But definitely, like once you do the measurements, you need to make sure that the power, the temperature level is the same, because the temperature will affect directly the leakage power and exponentially. Yeah.
Yeah, makes sense. Thanks.
Yeah, sure. So any other questions?
Yeah, I don't hear anything from Girai or Loise. Are there any other questions? Or from anyone?
So actually, there is a new question in YouTube.
Mm-hmm.
It says, is it possible to do the experiment using Verilog for instructions and SPI simulations to determine power?
Yes, definitely. If you have the implementations, you can do that with the simulation tool that like provide you with the power characterization of different instructions. So you don't need to have the measurements, but like in most, if you're talking about RISC-V, for example, it will be able to do that. But for like our commercial project processors, you don't have the RTL code for that.
Okay, thanks. Actually, there is another question that says, will processing memory technology reduce power consumption on CPU?
Yeah, but like on the CPU side, Onur can maybe you and Onur can talk about this more than me.
Well, I mean, it certainly could, right, by offloading more work to the memory side so that the CPU is less busy. But I think this sort of covert channels will remain unless you do something about them, right? Yeah. So it will certainly help with power consumption overall, I think, and energy consumption, but I don't think it will help with the covert channel issues. And also, I think if you have processors inside memory that have similar issues, you're also vulnerable to such covert channels on the memory side as well, right? Yeah.
Yep.
Then maybe Girai had some question. I saw his face.
No, I was gonna actually ask for the thing that you already mentioned, to question if we would have similar problems in the processor cores in the memory. But yeah, I think it's very intuitive now.
Okay, I think we may be at the end now, Jawad.
Yeah.
I don't see any questions unless someone has them or is seeing them. Maybe we'll wait for 10 seconds. But thanks for the seminar. I think this is an exciting topic. There are a lot of really interesting hardware security issues, new covert channels coming up, and we need to somehow design systems to be much more fundamentally secure so that we don't open up these holes going forward, right?
Yeah, right. Thank you, Noor, very much for inviting me to this talk. And yeah, it was very interesting talking in this live seminar. As always, like I like to talk in your seminars. And thank you all for your attention. So, like, please feel free if you to approach us in any questions or any topic that you would like to discuss in this area or other areas related to security power management.
Yeah. Okay, sounds good. Thanks, Jawad. And yeah, hopefully we will invite you back for your future works.
Yeah, sure.
Yeah.
Yeah. Thank you, Anor.
Yeah, take care.
Thank you.